In each atom, electrons are organized into orbitals. It is very tempting to think about orbitals as little pathways that electrons follow in their motion around the nucleus, but that is probably incorrect. Instead, you should view orbitals as simply allowed states of energy. And you shouldn't assign too much importance to a physical model of their movement around the atom. Now, orbitals themselves are organized into shells, which are classified according to this quantum number n, the principal quantum number. And for n equals 1, we have only one orbital, the so-called 1s orbital. For n equals 2, there is the 2s and 2p. For n equals 3, there is the 3s, 3p, and 3d orbitals, and so on. The simplest orbitals are clearly s orbitals because they're spherically symmetric. And so if we think about 1s orbital and look at its electron density here versus the distance from nucleus here, what we'll see is that the electron density increases exponentially as we approach the nucleus on either side. And looking at this in three-dimensional space, this corresponds to a sphere with a nucleus in the middle. And so this is the 1s orbital. 1s orbital, like any other orbital, can contain two electrons, and we represent this by showing two arrows with different orientations. But it doesn't have to contain two electrons, it can contain only one. And the first element in the periodic table is hydrogen, which has one electron and its configuration is 1s1. And the second one is helium, which has two electrons and its configuration is 1s2. As we move further into the shell number 2, now we start having more orbitals, and the second one is the 2s orbital. And 2s orbital is also spherically symmetric. And if we draw the same graph for the 2s orbital, we're going to notice again the exponential increase of electron density as we approach the nucleus. But at a certain distance from a nucleus, the electron density is 0, and then it starts growing again. So we get these sort of ripples of electron density. These points where electron density is 0, here and here, are called nodes. And we'll see that they're relatively important quantum mechanical constants. For our purposes, the 2s orbital is just larger than the 1s orbital. The nucleus is still in the center. And since it's larger, its energy is higher. Than 1s. Now, in terms of atoms that start filling the 2s orbitals, these are lithium, which now has its 1s orbital completely full, and it's 2s1, and then beryllium, which is 1s2, 2s2. This energy relationship between 1s, which is lower, and 2s, which is higher, is typically represented this way with them slightly offset and higher energy. But as we see in the second shell, there is also the 2p orbital. So we're going to draw that distribution over here. So the 2p orbital is different from the s orbitals in its symmetry. And the difference will become apparent right now when I tell you that this kind of an orbital has its node at the nucleus. And so the probability of finding an electron at the nucleus of a 2p orbital is virtually 0. There are 3p orbitals, and they differ in their spatial orientation. So this is the py, which is positioned along the y-axis. This is the px, and perpendicular to the plane of this screen is the pz orbital. And these three orbitals differ in their orientation, but not in their energy. So they have the same energy. And they're thus called degenerate. Okay? Now let's look at some of the elements that start filling up the p orbitals. These are boron, which is 1s2, 2s2, 2p1. Then element we're very interested in, carbon, which is 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, which has 2p4. Fluorine, which is 2p5. And finally neon, which is 2p6. Since we have only 3 p orbitals, and each one of them can contain 2 electrons, we stop with neon because there is no more space. Because p orbitals have electron density away from the nucleus, their energy is even higher than the s orbitals. And so if we're going to plot the energy of these orbitals, this will be 1s, 2s, and then 3 p orbitals which are higher than 2s but equal to each other in energy. The question is, how do we start filling up these orbitals? Clearly, if an orbital is lower in energy, it's going to get its electrons first. But what about the p orbitals, which are all the same in energy? So here we can have two different arrangements. If we have, for example, 3 electrons, we can put them up this way. Or we can pair 2 of them and then leave one of them unpaired. So which one is it going to be? Turns out that this is the preferred electronic configuration, and this is defined by Hund's rule, which says that in filling up these electronic orbitals, we should maximize multiplicity. And multiplicity is simply the number of unpaired electrons. Now we should maximize multiplicity only within the orbitals of the same energy. If orbitals have different energy, then we fill up the lower ones first and then go to the higher. The Hund's rule and in general the orbital parameters are on the basis of the periodic table of elements, and they're extremely important not just in organic chemistry but in all branches of chemistry. And to see why that is so, we can look at the first 2 rows of the periodic element, which have following elements in them: oxygen, nitrogen, fluorine, neon, and helium here. And then let's see what their electronic configurations are. So this will be 1s1, 1s2, 1s2, 2s1, 2s2, 2s2, 2p1, 2s2, 2p2, and so on. Sorry, nitrogen and oxygen have been switched. Now one thing that we see is that hydrogen and lithium have the same number of electrons at their highest level. Now their total number of electrons is different, but at the highest level they have the same number of electrons, that is 1, and these are called the valence electrons. It turns out that the chemical properties of an element are determined in large part only by its valence electrons and not by the electrons lower in energy, because the electrons lower in energy are happy where they are and they do not wish to engage in chemical reactions. And this is really reflected in the fact that hydrogen and lithium, to some extent, have similar chemical properties. Okay? On the other side of this segment of the periodic table are helium and neon. And although they do not have the same number of valence electrons, they share one other property, and that is that their valence electron shell is filled. So they have the filled electron shell. In order for them to get more electrons, they would need to start the next shell. And so these configuration of helium and neon are called noble gas configuration, because helium, neon, and their relatives further down in the periodic table are called noble gas. This configuration, because it's completely filled, is quite unreactive, because there is no reason for these elements to start the new shells only so that they will engage into reaction. And in the next section we will see how these full shells of noble gases come into play for all the other elements in determining their binding.